Hi, this is Aves from RIS. We are currently doing Unit 13, Electrostatics for our tutorials. We had completed our topic 13.1 in quite detail. From now on, I'm going to give you a rushed up version of the chapter because we have covered the most critical topic in the whole series. We are currently on our topic 13.2, which is electrostatic induction, and along with it we're going to discuss 13.3 because I consider it as a part of it, electroscope, because this is a very instrument how we get to know that electrostatic induction has occurred, right? So we're going to discuss this. Now previously we had discussed how electrostatic induction works, how charges are getting induced. Now we can also have different phenomenon where induction is not possible. Since we have discussed induction in detail before, I'm not going to go into detailing induction again, but I'm going to give you the fact that there are ways in which induction can also be avoided. Because why this is an electrical hazard. Most of you have seen, like those of us who have seen those old big TVs at home, which were very old, classic, glass displays, crystal, and very bright, and consumed a lot of electricity with a lot of heat being generated. They were known as the CRTs, cathode ray tubes, right? Crt televisions, Crt TVs, old crisp displays. Now this is a very critical device in a way that at times when you were barefoot and you would touch that, let's say if our sticky man is going to try and touch it, right? If he touches this, he's going to get electrocuted. Why? Because the surface of this glass used to get charged, and we used to call this that this is charged. We got electrocuted because of the static charge, right? You must have all heard this if you haven't had these. Though those of you who have seen these old televisions, they would know about this static charge, because I'm pretty sure anyone who's ever seen these CRTs, they must have touched the surface of the glass, and they all must have got the tiny little electrostatic current that they get after touching it once they ground it. So I'm using the word ground. Keep this in your head, right, before we move on. So those CRT televisions, they used to deliver this electric shock of electrostatic charge which was on the surface. And why this was induced? Because this cathode ray tube used to have this inside, let's make an inside view of this, had a cathode ray inside it. It was a glass tube which was at vacuum. Actually, it was a very expensive device as compared to the LCDs or the LEDs we are currently having. These used to be very, very expensive devices actually, and nowadays if you get one of these, it's as a new device from a manufacturer, oh god, it's gonna cost you a lot, because these are very, very expensive devices nowadays. Back in those times, they were considered much expensive because the material available was in abundance. Nowadays those materials are not abundant, so there used to be a circuitry behind it from which the image or the antenna used to rise up, right? The receiver is there. So what happened, the signal would be sent as current, right? Current, or you can say electricity was given to this cathode ray tube which was at vacuum, and there was an electron ejector over here which used to throw electrons at this glass boundary. And what would happen, that there was a special powder or special coating which we call as fluorescent coating. It was used to be coated on these on the insides of these glass screens. It would get bombarded by these electrons, and each frequency of electron, now most of you have read the wave motion chapter, each different frequency of electron was thrown representing different colors, and once they would fall, they would release different energies, right? We do know that change in frequency means change in energy of the particles, right? So different energies means different color or different wavelengths are going to get generated, right? So we used to get to see colors because of the change in the frequencies of these electrons projected, and hence the CRT used to give us a colored image. Usually in the beginning they were black and white, later on they were 16 colors, then 32 colors, and 256 color was the highest that was achieved on CRTs. Nowadays, I mean, even your cell phones have 16 million colors, right? You know, far ahead in technology. But since there was a huge number of electrons bombarded at the base of it, so there would be positive charges of the air would get attracted to this surface, and the electric shock that you would get was basically because of the positive charges that you were getting. It wasn't actually negative charge, it was positive charge. And why? Because there was a lot of negative charge being bombarded at the base of it, and this coating and this glass sheet wasn't that much thick. And I mean, those of you who had accidentally broken one of the CRTs, they would know this. It used to be a hollow big tube which was black inside, and the glass is very delicate and very thin on the front. So that is why, due to the electron bombardment, there's charge being induced on top of the glass, and once you touch it, you get electrocuted. So this is what grounding is, right? What a ground is that you provide charges or a charged particle a method to neutralize itself. You provide a medium to neutralize, right? Neutralize a particle. So once you talk about neutralization, you mean that if there is a positive, you are simply sinking it in a pool where there is enough positive and negative charges that they can incorporate any amount of charge thrown at it, right? It doesn't matter, it can incorporate more charge without getting to show any charge on the surface, right? This is what we call as ground, right? What is ground? You must have seen there is a green wire in your domestic wiring, which is kept as a safety to provide short circuit, a better method rather than short circuiting your walls. The excess short circuited amount of current is passed down into the ground using a ground cable, and that is what you have seen. It is represented by the symbol you must have seen in some of the electrical devices, this symbol with these bars, right? This is what you see as ground or as neutral. This is also written as N or as G on electrical devices. Very common. You can see it on your charger as well, that there's a ground wire and there's a positive wire, or there's a negative wire, or there's a ground wire. You know, many configurations, many manufacturers have their own symbology along with it, but usually ground provides a place where charges can go to rest, right? Entirely disintegrate and be forgotten, so to speak. So continuing on, that how this is actually the opposite of induction, what I was trying to talk about, that if you want to avoid induction, you want to create a ground. And why this is important, that if you don't create ground with other surfaces, like on the LCD, LCD has its own ground. That is why this phenomenon is not happening, even though even in LCD there's a bunch of electrons on the behind the surface of your screen, but you don't get to feel this electrocution problem in LCDs or LEDs. Why? Because they have proper grounds now. Back in those days, ground wasn't considered much of an important feature in electrical devices, but you know, after getting electrocuted, and some, like if this was a much big, like 80-60 inch display, you're going to feel a very powerful electric shock, right? You might actually get shocked up for 15 seconds because of the amount of charge that would be there. From a small screen, it was just a tiny little shock that you'd feel. So to avoid induction, we use ground, right? So if for example, In the previous cases where we had glass rod, this is a conceptual question in the exercise, unfortunately not a part of the federal board regime, but we're going to discuss it because it's a very important question. That what will happen if I take this glass rod, I charge it, this is glass, right, and I take another rod which is metal, right, which is metal, you can say, and this is also positively charged, or anything negatively charged, doesn't really matter, right, both of them are positively charged. Now considering that human hand is actually conductive, and conductive at obviously we get to feel the huge amounts of current at a specific critical level of voltage, but we do get to feel electrostatic charges, right, because at tiny level they are at their energies are at giga electron volts, which is very very high energy, but the current produced by it is very small, so we don't get to feel much of the shock because of these. We get a tiny little tingle because of these charges when there are very very little amount of charges available. More the number of charges, more the powerful effect of the tingling, and up to a point that you might even get an electric shock because of it, if the number of charges are too much. Now what will happen if I take I simply hold it? What happens that if I touch the glass rod, the place where I've touched the glass rod, right, let's say I've touched here, only the charge in that area is going to get grounded in me. Why? Because this is a very small charge and my body is providing a very huge space for that charge to move around, so I've become pretty much a ground for it. Although for very strong I might not be a ground, I might be much of an insulator. So the word insulation is for electrostatics is a little bit absurd. You can say it's a more complex idea than we usually know about insulators, right? So when we talk about ground on glass, the place where I've touched, let's say this is where my fingers were out of my hand, right, I grasped it from here, right, so the charge on this area is going to get disintegrated, this one as well. Let's say I touched it with my thumb, right, but rest of the charge, if the whole rod was charged, rest of the charge on top of it, on there or here, all of this charge will be available. In terms of metal, since we do know that metals are electrical conductors, that means charges can easily flow around them. So if I touch this even with a point of a finger, all of these charges are going to get transferred to my finger, because my finger is now providing a much bigger place for them to run around. So all these charges are going to get finished, and this is what we call as ground. So I have grounded both these objects. In case of objects which are insulators, electrical insulators, if they are charged, they only get discharged at a place where I've touched, right, where the charges could interact with my hand. Here the charges could freely flow because this was an electrical conductor itself, so I simply touched at one point and all of the charges flew into my finger and eventually into my body, and if I'm barefooted, then eventually into the ground, right. So this is what grounding is, and this is one way, and to avoid currents like this. For example, if this was a very heavily charged piece of metal, then I would definitely going to get electrocuted. So better way is that I create an external ground for this kind of an object which is getting frequently charged, and it might electrocute someone who's unaware of this metal being charged. We can simply provide an additional ground to keep any excess positive charge which gets induced on the surface to get into ground, and then my finger is going to be safe because there will be no charge sustained on the surface for a prolonged time. As long as the ground is there, I'm not going to get anything. Why? Because remember this, charges when they're going to ground wish to have shortest path to ground. Now this is a reality of physics, right? This is a fact which cannot be avoided. The charges will always try to find the shortest path. In this case, since ground is a lot bigger sink or pool for my for the charges on this metal as compared to my finger, then obviously this is the shorter path for them to go into ground, because my body is not a good conductor, although it is a conductor of electricity, but it is not as good a conductor as much as if I take another conductor and make it as a ground for the charges for them to flow into the ground and neutralize themselves, right? So this is what you need to do to avoid the electrical hazards by making a ground, right? To avoid any electrostatic hazard. Now this is although the very end part of the chapter, but I think we need to discuss things in a more rigorous manner than being in sequence, so that you get to know stuff in correlation rather than just as tiny topics to answer certain questions. You should have a better understanding of the subject as a whole. Now moving on to electroscope. Now electroscope is a very simple device. Let's say I have a glass bottle. I've taken one tiny wire. I've attached two platinum or any thin conductor. You can even take aluminum, gold, or any metal, but they've used gold foils because why? Gold is a little easier to mold to make it into a very thin sheet. That is why gold foil is used. Even platinum is used, and more expensive models of electroscope. What is an electroscope? This is the touch area, the touch pad, where you can bring the object and test whether this has any charge or not. Now since these are very thin, freely moving plates, when there is no charge, these plates are hanging towards ground. Why? Because of the weight. Gravity is acting on them, so the plates are going to stay in a vertical alignment. It's not going to get moved around. But if I bring a positively charged rod and I touch it on this, let's say this is a piece of metal which was positively charged, then what will happen? All of these positive charges are going to consider this as a ground, neutral. Currently this is in neutral form, so if I touch it, it is going to get, these gold foils are going to get repelled. Why? Because now they are both having same charges. Why? Because the electroscope is now charged. I have charged this conducting point by touching my object with this, which was positively charged. Since the glass electroscope is neutral in the beginning, all the charges, positive charges, will flow into the electroscope as well, and this is a very small ground. Small ground means it can incorporate even a very tiny amount of electrostatic charges and still show you the deflection. Now these you can say gold foils have repelled each other. They have opened up. Same way, now let's go to the third step. Since we have a charged electroscope, unless we ground this electroscope again, it is going to remain positively charged, and that's the fun part of it. Why? Because this is a vacuumated tube, and the only entry is through this hole in the glass, which is sealed after vacuum generation of this tube. So this will remain positively charged from inside unless you ground it from the top, right? Then nothing is going to happen inside unless you ground it. So what if I bring a negatively charged rod over here? Now this is going to get interesting. Why? Because now we know both positive and negative, if brought together, they neutralize themselves, right? If I take a positive particle, if I take a negative particle, and bring them together and let them interact with one another, they become one neutral particle, which usually a neutral particle would be an example of hydrogen atom. But since these are not atoms, these are partial charges, they will simply destabilize themselves. That means dipoles which are currently induced by these will get neutralized. Their poles will get resettled into neutral positions, right? For example, if the atom was in this position currently, let's say this side is negative, for this all the positives are on one side, we can say we have charged with independent positive charges, and we have dependent or both independent, like these charges. If we touch them together, they will flow together, and what will happen, it would come back to neutral position, and this is what the whole sequence would look like, right? This is neutral, right? So if I take the positive, if I take a neutral glass tube, I charge it with positive, it becomes opened up, because now this is also on positive charge. If now I take the positively charged tube and take the negative around it and touch it, they would neutralize up to a point that there would be no charge on either. Considering the fact that the number of positive charges and the number of negative charges on both of these, they are equal, number of charges are equal. If they are equal, it would get diminished. If they are not equal, then obviously whichever has more charges would retain its charges and will obviously induce charge on the other one as well, right? But let's consider an ideal case where this rod and this electroscope are having equal number of charges. Although I have drawn 3, but here are more, but consider that they're equal, right? So if they're equal number of charges, they will neutralize themselves, right? The same way ground was happening. So this is how you can use an electroscope to detect a charge, to know whether this rod is positively or negatively charged. If I now consider the fact, if this was a positively charged, what will happen? Can we get this? No, we're not going to get this. Why? Because now these are same charges, they will try to repel each other, but they have no space to go and they have no other space to go. Even if I touch them together, there's nothing going to happen to them. Why? Because they're same charges, these plates will remain open. That means the charge on this electroscope is same as that of the rod, right? But if we see something like this happening, let's say this, if the electroscope closes its foils after being positively or negatively or any charge, if we know that this is getting, let's say you don't know whether this is positive or negative, but I'm telling you that both of these are charged, right? You don't know whether this is positive or negative, right? Let's remove these. Let's consider this as a separate case. Consider this fact, that if we are having an electroscope which is charged, how do you know it is charged? Because these flaps are opened up. When they're opened up, that means the electroscope is charged. Even if you don't see charges, or even if I don't write charges, you should know if the flaps are open, then these gold foils are open, then it is charged, right? This is charged. You don't know whether this is positive or negative. No idea. Over here, you don't know either. But if I touch it and the foil closes, that means these two had opposite charges. These two had opposite charges. Why? Because they got neutralized, right? After touching with this, the electroscope is neutralized, and it would only neutralize if the charges are opposite. But if they are, if I don't see anything in terms of closure of these foils, these foils don't close down, that means that this rod and this electroscope, they had same charges, right? If it remains opened up even after touching this, then the electroscope as well as this rod are having the same charge. If this closes down, then they have opposite charges, right? Now this is how you use an electroscope to identify charges. Even if you don't know whether the electroscope is positive or negative, you can easily identify one thing, and you can start by touching something which you do know is positively or negatively charged. For example, glass rod, if rubbed with silk, always results in a positive charge on glass rod. If I touch this with glass rod first like this, I would know that this is positively charged, and then I can check whether this is positive or negative using this electroscope experiment, right? I hope I was able to help you understand how induction and electroscope is working in our daily life, and how these are linked with others, phenomenon which we see in our daily life, like CRTs or electric shocks or electrostatic shocks we get to feel each day, right? Please leave your comments if you have any issues understanding this lecture, so that I may be able to give you a better feedback and respond to you accordingly. Thank you.